Hi everybody, my name is Benjamin Hege. I'm a software developer for the South African Radio Astronomy Observatory. We are continuing on our series on interferometric measurements and how we perform calibration and imaging with these large array-based telescopes. Now, the topic of this discussion in particular is the imaging section. So, what we're first going to be looking at is the special relationship that's called the Cittert-Zernike theorem that takes us between visibility space and imaging space. Now, at this point in time, what you should have looked at already, if you're not joining us live, is the mathematical background section coupled to interferometry, and that especially includes the Fourier transform, so you should have looked at all the properties for that as well. Then you should have looked at the visibility space, so remember that the interferometer measures the spatial coherency domain of a sky distribution, and that measurement we refer to as visibilities. What you should also have looked at already is the radio interferometric measurement equation, so-called RIME. Remember that the RIME just describes the various different effects of this systematics and environmental effects on the propagation of the signal that we're trying to measure. And then lastly, coupled with that the RIME is interferometric calibration. Now, let's recap what we mean by a convolution. A convolution is, simply put, just a mathematical operation that takes a function, let's call it f, and another function which we'll refer to as a kernel function, let's call that g. It integrates over the function as you pointwise multiply the kernel function with function f and slide that kernel function across the function f. Now, in the Fourier space, remember that the convolution is a multiplication of those two signals. And a simple example of where this is actually used in everyday life is if you think about computer vision. A blurring operation can be described as just a convolution of the image with a simple two-dimensional Gaussian function. Another example is, let's think about the COVID statistics that's being generated for us. So a 7-day average, for instance, can be stated as a convolution of a boxcar function with the statistics captured daily and that boxcar function has a width of 7 days in this case. So let's have a look at a very simple example here. Our input signal here is a Dirac delta, and we are convolving that with a Gaussian. Now, what are we going to get? Well, the result is just a shifted Gaussian, yeah, right? So then let's go back to the visibilities just to recap what the interferometer measures. Remember that the interferometer measures an intensity as emitted by a source out in the far field, and the delay between that signal reaching an antenna, let's call that P, and another antenna separated by some physical distance, let's call that antenna Q. Now, in this case, we have a single measurement. The measurement in this case lies somewhere on the UV plane, and in this case it is just along the UV axis at some distance. That distance is given by the projected baseline length, right? This is a short distance in this example, and if we think back to the measurement taken by the interferometer, remember that we measure the intensity multiplied by the complex exponential for a complex interferometer. So this has the effect of projecting a fringe over the sky. Now, because this baseline is short, the projected fringe has a long period. So, and that will result in the fringe being sensitive to the broad scale structure on the sky in this particular instance. Now we look at the case where we move the antennas further apart, so along the same direction. You see that the fringe now becomes much more compact. And if you integrate over that fringe, it has the effect of being sensitive to all the very fine scale structure in the image. So things like points and edges on the sky. Now, let's consider something that's more complex. Remember that if we only have a single measurement with two antennas, then that fringe doesn't tell us anything about the second axis. So for that, we really do need more samples within this UV space. Let's consider the VLA in its most compact configuration, the deconfiguration, as we show in the picture on the left-hand side there. Along the furthest regions of this UV space that we're sampling, we see that we measure the more fine-scale structure with the array, and the long baselines then therefore lies towards the edge of this space. Towards the center of the space, we have all the short spacings between the antennas. All right. Now, as I said, the edge measures of the space measures all the fine scale structure, so the rapidly varying structure in the sky, whereas the center measures all the broad, fluffy structure in the sky. Right at the center of this UV space, we have a mean value, which we refer to as the DC component as well, for all the engineers out there. And what we typically do is we discard this measurement. Why do we discard this measurement, you may ask? Well, the thing is, if you remember that we're cross-correlating pairs of antennas here, right? So the only way we can get to a origin in this space is to correlate antenna P with antenna P for all such antennas. Now, that in effect correlates the same noise that's measured on antenna P with that same noise, right? So the noise won't diminish in this case, and this is why we typically throw out those measurements. There is some areas in science where we actually want the really broad scale structure, so things like H1 intensity mapping, where we would need to use these very short spacings around the origin, and in that case we typically use a single dish to measure that. So that's about the only area where we actually use that measurement. As you can see, we fill up the UV plane here with adding more antennas, and we'll get onto techniques on how to fill up the plane just a bit later on. But in all areas where we don't have measurements, it actually adds uncertainty about the spatial frequencies, right? So we don't take those measurements, we don't have that information, and this reflects in the image as an elongated response in that particular direction. So in all the areas where, as indicated by this purple line there in the center of the image, we don't have measurements, and it adds this uncertainty. The other thing that we need to point out here is what we're measuring is a real valued function, right? We're measuring just an intensity with some phase, right? So that intensity itself is a real valued function. So whether we measure the function with a baseline projection PQ as opposed to QP, doesn't matter. It adds no further information, and this space is therefore remission, right? So the conjugate is equal to the conjugate baseline is equal to any chosen baseline that we take. So now you might ask, how do you go about selecting the resolution at which to sample? Well, this is given by the Nyquist relationship in a low signal to noise environment. So the chosen resolution for our image has to be the reciprocal of the longest spacing. Here we indicate that spacing as the number of pixels that we chose for our image, times by the delta in both U and the V spacing. And remember that it needs to be twice that size at the very minimum. Normally what we do is we oversample that space so that we place a few pixels of response for every point-like source out there. Now, coming back to a more formal definition of the space, so we've already alluded to taking cosines and sines of per point source out there on the sky. So we've alluded to this being a Fourier transform. Well, we can more formally state this as the van Cittert-Zernike theorem. Now, all this theorem says is, if we take a measurement on a projected plane where the W basis is set to 0, remember that W points towards the source that we're trying to measure. So normally that is at our fringe stopping center of the array. This is just a integral over the entire sky of all the contributing intensities and their respective delay offsets from the fringe stopping center that we choose. So in a typical scenario, we would inject another delay term, so another complex exponential into this equation to fringe stop anywhere on the sky that we would like to have a maximal response. The basis here is, as we have already indicated, is this UVW space, which is the local observer's horizon, where W points towards the phase stopping center, as we already discussed. And then the cosines L, M, and N, where N is just on the sphere, and N points towards the source, towards the source that we're trying to measure, so our fringe stopping center. So the N term here is indicated there in the reciprocal of dLdm. It is just the determinant of the Jacobian, because we're shifting between a solid angle integral and the integral in Euclidean space. And this, my friends, is essentially just a two-dimensional Fourier transform. Now, I should point out that this particular relationship only holds for arrays that is aligned perfectly east-west. As soon as we add components in non-east-west, so north-south direction, then this relationship breaks down. So why is that? Well, let's look at the sampling that we get over time. Remember that the interferometer captures the spatial projections, and because the Earth spins underneath the sky, we capture the same spatial frequency along different projections of this baseline as it rotates underneath the sky. Now, with a perfectly aligned east-west interferometer, as we indicate there on the right-hand side, all the samples lie on a single plane within this continuous 3D space. For a 2D interferometer, so where we move even just one of the antennas in a north-south direction, still on a perfectly flat plane, we get samples in we get samples in different planes within this 3D space. Now, that is a problem because that essentially adds, as we can see over here, that has essentially different projections per such spacing onto this W0 plane. Now, for an east-west interferometer, we can just apply a single linear transformation to all the visibilities to bring them back onto a projected W0 plane, as we can indicate over here. Here, we simply decompose the Wn-1 term into new coordinates for L and M prime, and this relationship is still a two-dimensional Fourier transform. Now, let's look at the 2D interferometer in the case where we take measurements over a wider field of view. Now, in this case, the delay that we're measuring of the signal propagation between an antenna P and antenna Q depends on this Wn-1 term, right? So the issue here now is that for each different spacing, north-south spacing, this Wn-1 term has a slightly different tilt to it. If you recall back to your Fourier theory, a delay introduced in one space is a shift in another space. This is completely going to screw up our image, right? Because the different interferometers within the array now measures the signal at different tilts, right? So each is going to introduce its own bit of shifting in the sky. The solution to this problem really is twofold. We're either going to make the field of view smaller, right? That's what we call faceting. So we break up the field of view into many small bits of sky, and we phase steer and fringe stop essentially at the centers of those individual bits of sky. This removes this combination of the Wn-1 term. Alternatively, what we could do is to convolve that term back in, either in the visibility space, so the spatial coherencies, in that case we call it W projection, or in the image space, in which we call it W stacking. That essentially removes the error contribution from neglecting that Wn-1 term, as we would have done if we only took a two-dimensional Fourier transform with a array that contains north-south spacings. The other way of doing this, so the third way, is to just make snapshot images of the sky. So we point and click almost. So it's like, let's say we take observations at an interval of 5 minutes, and this essentially constrains the samples that we collect to a particular plane for that duration. So almost a single plane. So that also removes this error to some degree. We can combine these various different mitigation methods in any way we wish. So we can do W projection, for instance, coupled with faceting, as we do in the facet imager, or any other combination of these techniques. Now, let's look at the real-life example and the kind of structure that we expect to see if we neglect this Wn-1 term. Now, we observed a supernova shell here in the galactic plane with the VLA, in this case, in its DNC configuration. The source sitting off the center of the image there, so where the phase stopping center is always defined to be at the center of the image, so it's far off the phase tracking center of the interferometer. That source is going to be subject to these wide field effects. Now, for a source that is non-corrected, in this case, you'll see this kind of horn structure around the source as it's being smeared out by the various different spacings within the array. if we correct for it by applying a W projection, W stacking in the WS clean imager, for instance, or faceting, either in DFacet or older software in APES or CASA, for instance, then we'll see that the point source is essentially brought back to an unsmeared state. So what should have been a point source here in the corrected image, we can clearly see is very smeared out with this very typical horn-like structure. So I'm not going to go into much more detail about how these techniques actually work. For that, you can look at the interferometric measurement book. The fine details is discussed in this, but the take-home point of this is just to enable your wide field corrections in your chosen imager whenever you have a two-dimensional array such as Meerkat, ASCAP, GMRT, and so forth and so on. It is not required to enable it if you're working with archival data of the Westerbork synthesis radio telescope, which is almost perfectly aligned east-west. So that is the only thing that you should take into consideration at this point. Now, let's look at the limitations of this Fourier relationship. So this, the applicability of the Van Cittert-Zernike theorem to convert between the visibilities and the image spaces. Now, the full relationship is described here in the equation at the top. Now, it says that the measured visibility is essentially subjected to the far field response of our antenna, so which some refer to as the A term or the E term in the rhyme, multiplied by the intensity, multiplied again by the complex exponential for a complex interferometer. The delay term here, as I said, depends on the L, M, and N cosines as projected onto the baseline in the UVW space. What we need for this relationship to hold, as I said, is, we need a small field of view approximation or a way to recover only approximate coplanarity of the measurements, right? We've discussed how to do that already. The relationship also only holds if the various sources on the sky is emitting radiation incoherently from one another, right? So they're individual sources of essentially thermal and synchrotron noise, right? We also rely on the far field approximation in this case, right? So remember that between antenna P and antenna Q, we measure a delay, but that delay depends on that a planar wave coming into those two antennas. So that only happens if you place the source far away, right? Then we also rely on a narrowband approximation. So our channelization of our signal, so within the frequency space, needs to be much smaller than essentially our resolution element. And the fractional channel width therefore needs to be much less than the bandwidth that we're trying to capture with the instrument. And then also notice here that this is a continuous sampling in the UV space. So in this form, the relationship really only holds if we have continuous samples at infinitesimal spacings apart out to infinity. So of course this is not going to work in reality, and that introduces a sampling response to our instrument, which we call the PSF, and we'll look at that just now. All right. So in its most essential form, this basic two-dimensional Fourier transform only holds for the east-west interferometer, as we pointed out.